Challenge accepted. I went down the AI energy rabbit hole for you, and I found something that seems, well, I think it seems pretty simple. Model size determines compute. Compute determines energy use. And energy is becoming one of the biggest constraints in AI. So I believe the next breakthrough needs to come from re-examining the AI architecture itself under our models. This is what I'm finding. Our human brain runs on about 20 watts of power. A single high-end AI training chip draws about 600 plus watts of power. A mega AI data center draws about 100 million watts of power. Biological intelligence achieves learning, memory, prediction, adaptation, pattern recognition on a radically smaller amount of energy. It's kind of the big dust stamp, literally on our forehead. That comparison is the reason I went down the rabbit hole of brain-inspired AI. Started with Drosophila, a fruit fly whose brain is roughly the size of a poppy seed, to understand how biological intelligence does so much with so little energy. Scientists map the physical wiring of Drosophila's brain as about 139,000 neurons, more than 50 million synapses, and they could study a working brain as a measurable circuit system. How information moves, how signals activate, how memory forms from the wiring itself. The project is actually called Cortex AI and is being built by Flourish, a neuroscience-driven startup. They raised about 500 million at a reported 2.5 billion valuation, and of course, Jeff Bezos. The goal is to understand why and how our biological intelligence learns and adapts with a fraction of the energy our AI models require. They are focused on what we call the neocortex, structures called cortical column. A cortical column is a repeating structure in our brains, roughly half a millimeter wide, containing about 10,000 neurons. And the theory is that cortical columns may act like the brain's fundamental computation unit. If Flourish's theory holds, it changes the conversation around the architecture and the energy. The question becomes how information is stored, processed, activated, and updated. And the research is pointing to three major differences. First, the brain computes where data lives. What that means is our synapses stores information and helps process it inside the same neural structure. Our memory and computation are co-localized. Current AI has what we call the von Neumann bottleneck, right? And that's where memory and processing are actually separate. If you're unfamiliar, information is stored in RAM, SSDs, databases, and other memory type systems. And then it's processed by CPUs, GPUs, or AI accelerators. Every operation currently requires moving data back and forth, and the movement costs energy before our systems even use that information. Second difference that we're finding, the brain fires sparsely, which we know. Only a small percentage of your neurons are active at any given moment. The brain activates what it needs and then leaves the rest quiet and still, conserving its own energy. In computing, we would call this sparse coding. Many of the large AI systems activate enormous parameter networks during inference, using more computation than a smaller, more selective system would require, for instance. So the brain's efficiency comes partly from selectivity. Third difference, the brain learns continuously. Most AI models are trained, deployed, and updated later through retraining, fine-tuning, retrieval systems, or external memory. They can incorporate new information, but they don't naturally learn from ongoing experience the way we biologically do. When artificial systems absorb new information too directly, they actually overwrite their prior learning. We call this catastrophic forgetting. The brain addresses this through memory consolidation. That happens in your hippocampus, and it helps replay important experiences and integrates them into your long-term memory. Think about learning to drive a car. You do not forget how to drive every other car you have used before. You adapt what you already know, and you add new details without erasing your old skills. Flourish says it has already built a hippocampus-inspired memory system that allows AI to learn continuously from small amounts of new data without forgetting prior knowledge. That is the whole technical center of Cortex AI. Memory closer to computation, activation where it's needed, and learning that keeps updating without starting over. AI needs to be more efficient, and it needs to be more efficient in its architecture itself. A system that runs closer to 20 to 50 watts, like a light bulb, moves advanced AI towards a device level energy use instead of these huge massive data centers dependent on compute. That changes the entire economics around it because it challenges the assumption that AI's next leap has to come from making everything larger and bigger. Bigger models have proved AI's concept. However, I think the next evolution should come from understanding how our biological systems organize computation, learning, and memory.